So Euler get famous by solving this problem. It's called the Basel problem. So he wants so what is the value of this 1 plus 1 over 1 square, 1 over 2 square? So what is this? So this is actually the, if we are using the notation that we know nowadays, so this is going to be the Riemann-Zeta function for the case s is equal to 2. Is that okay? So what is it? So why is it called Basel problem? So Basel is a small town in Switzerland. This is the place where Euler is born. This is as far as I remember. And then there are a lot of famous mathematicians actually from Basel, and it has the one of the oldest university in Europe. So like what? Like Euler's advisor Bernoulli. So the Bernoulli family has many Bernoullis. So there's the Jacob Bernoulli, there's the Joseph Bernoulli, yes, Jacob, Joseph, yes, and then what? Daniel Bernoulli, and then a lot. So there are a lot. Okay, so like father and then son and then siblings, like the uncles and then daughters, something like this. So a lot of them. So Bernoulli get famous. So this Jacob Bernoulli or Joseph Bernoulli got famous for a long time, but still this is still an open problem. No one knows how to solve it. And then Euler finds that this is amazingly, it is equal to. So first of all, this is bounded. This is bounded. This is bounded. The reason is what? So the reason is that this one is less than 1 over 2 square. This one. If you look at this term, and then for the following, four terms, 1 over 4 square, 1 over 5 square, 1 over 6 square, and then 1 over 7 square, they are all less than 1 over 4 square. Is that okay? And then for the following 8 terms, every one of them is less than or equal to 1 over 8 square. So in the end, this one will be less than or equal to 1 plus 2 terms of 1 over 2 square, so which is 1 over 2, and then 4 terms of 1 over 4 square, which is 1 over 4, and then 8 terms of 1 over 8, which is 1 over 8 square, which is 1 over 8, and then and so on and so forth. So this will be less than or equal to 2. This is what we know. Is that okay? So this is bounded. And moreover, if we add more terms, then it will become larger and larger. So this is going to be a function. If you stop at a certain value of n squared, so this is going to be an increasing function in n, and then it is bounded by 2 at the top. So that means that the limit of this will exist. So at that time, okay, people knows that this will be converging to a certain value. And what value is this one? So this will be equal to, interesting, very interesting. This is going to be pi square over 6. Okay, the pi that we know, the circumference over the radius, the ratio between that. Okay, so this is 3.14 blah blah blah. The square of this one is something like 9 point something divided by 6. So the result is like 1.5 or 1.6, somewhere around that. Okay, so Euler got famous about this. And then as you know, so we just have one fascinating result that relates the summation of this thing, 1 over n to the power s summation, related it with the product of factors that is coming out from prime numbers. So yeah, if I have time, I will tell you more about this one later. Okay. Now, so today we don't have so much time, but that should be able to deliver to you an idea of solving So we want to, so we are still about solving linear recurrence, but then in one part we are stuck. Okay, we are stuck with the so-called homogeneous equation, right? The homogeneous solution. So because homogeneous solution represents zeros, and then we need to know how the zeros look like before we can get the general solution, or we call the total solution. So this time, let's try to solve the homogeneous recurrence solution, or the solving the homogeneous recurrence of that one. So let's take an example. So let's take an example of a recurrence that looks like this. Let's say an, this time minus, let's say 5, an minus 1 plus 6 an minus 2 is equal to 0. Okay, today, let's say we are going to solve this one. This recurrence has something special. It is equal to 0. So the function of n is equal to the constant 0. So a good thing about this one is that we can guess a particular solution super easy. Just guess an is equal to 0. Because 0 minus 5 times 0 plus 6 times 0 is equal to 0. So for this kind of recurrence, the particular solution is super easy. But then we want to find out what is the, how is the homogeneous solution look like. So a standard trick here is we create a characteristic equation. So the characteristic equation is like this. So if it is starting from an up to an minus k, we will use the term x to the power k to represent an. So here, there are 1, 2, 3 terms, and then it goes from n up to n minus 2. I'm going to use x squared to represent it. Okay, and then this is x squared, and then we are going to use x to represent an minus 1 somehow. And then somehow, for this one, I'm using the constant to represent it. So this is the so-called characteristic equation. So what is the purpose of setting up a characteristic equation? We are interested in solving the characteristic equation first to get the roots of the characteristic equation. Okay, so for this characteristic equation, we can see that it has two roots. What are the two roots of this one? This is a quadratic equation. Two roots are 2 and 3, right? Okay, so this is actually x minus 2 times x minus 3 is equal to 0. So we can have x is equal to 2 or 3. Okay, so what is good about this root? Okay, once we get a root, we can find that if we set an is equal to the root to the power n, okay, what will happen? Okay, then let's take a look. Okay, let's set an is equal to 2 to the power n. Then we will have an minus 5 an minus 1 plus 6 an minus 2 is going to be equal to 2 to the power n minus 5 times 2 to the power n minus 1. Is that okay? Plus 6 times 2 to the power n minus 2. Is that okay? And then this is equal to, yeah, we can solve it, but before we solve it, let's take the 2 to the power n minus 2 as a common factor outside, and then what we have here, we will have 2 squared minus 5 times 2 plus 6. Is that okay? And look at it. This is going to be 0. This is going to be 0. Why? Because 2 is the root of x squared minus 5x plus 6. Is that okay? So this will be 0. So this is one of the case that we can set it to be 0. Is that okay? And moreover, let's do something more complicated. A little bit, just a little bit complicated. Let's make it a times 2 to the power n rather than 2 to the power n. Let's make it a times 2 to the power n. Then what will happen? Then we will multiply an a here, right? Right? And then this will multiply, this becomes 5 times a times 2 to the power n minus 1, right? And then this will become 6 times a times 2 to the power n minus 2, right? So in the end, we will still be able to take out a times 2 to the power n minus 2. And then it is equal to 0. So we see that a root, if we can find the root of a characteristic equation, then suddenly we know a lot about the zeros that we have. Anything that is of the form a times 2 to the power n will make the recurrence okay. Is that okay? Okay, let's try another one. So this is the case where a is like this. So let's try another root. So the other root, let's try, this time let's try an is equal to b times 3 to the power n. Okay, then what will happen? Then an minus 5 times an minus 1 plus 6 times an minus 2 will be equal to b 3 to the power n. Is that okay? Minus 5b times 3 to the power n minus 1 plus 6b times 3 to the power n minus 2. Is that okay? And then we take out what? The same as before, we take out b times 3 to the power n minus 2, and then what is left? We get 3 squared minus 5 times 3 plus 6. Is that okay? And again, you can see, suddenly, this is about the characteristic equation. That's why we are solving the characteristic equation. This is going to be 0. Is that okay? So that means that if an is equal to b times 3 to the power n, then everything will be okay. The recurrence will be satisfied. Is that okay? Now what's more is that, so if you are okay with this, then the combination of these two, if this time I set an is equal to a times 2 to the power n plus b times 3 to the power n, then what will happen? Then the formula, the recurrence, will still be satisfied. Is that okay? Because those getting from the a part will be evaluated as 0. Those related to b will still be evaluated as 0, right? So each time you put an is equal to this one, then you have a blah 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 plus b blah blah blah, and then minus 5 an minus 1, so minus 5 bracket a blah 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 plus b blah 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 bracket, right? And then plus 6 bracket a blah 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 b blah 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 close. So all the a parts get cancelled, it will become 0. All the b parts will get cancelled, will be 0. So it will be equal to 0. So the recurrence will be satisfied. Is that okay? So in that case, this will be the form of a homogeneous solution. And actually, this is the exact form of a homogeneous solution. The reason is why. So if you look at this an minus 5 an minus 1 plus 6 an minus 2, we see that if we specify two starting conditions, let's say a0 is equal to something. Let's say a0 is equal to 1, a1 is equal to, let's say a1 is equal to 2. That's what we know. We know that the whole sequence will be fixed. Because I have a0, a1, I can use the recurrence to get a2 specifically, uniquely, right? And then now I have a1 and a2, I can get a3. Is that okay? So once we specify two starting conditions, then everything will be precise, uniquely defined, well defined. Okay? So somehow, this recurrence has like degree of freedom of 2. If I fix one thing and then fix another thing, then it is fixed. You cannot change. So similarly, if you look at this form, there is the degree of freedom is also 2. If I tell you what is A and what is B, suddenly this an will be defined. So in that case, you cannot change anyway. So the degree of freedom of the original recurrence is 2, And the degree of the freedom of your solution here is also 2. They match. So it must be the solution of the original equation. Is that okay? So general strategy, if we have a homogeneous solution, if we have a recurrence that is in this form, is equal to 0. We want to get the homogeneous solution. So what should we do? We first set up the characteristic equation, get the roots, and then establish the solution in this form. Now, once we have this form, then it depends on what we are going to do. We are going to match with the boundary condition so that to figure out what is the value of A and what is the value of B here. Is that okay? So for instance, in this example, let's say A0 is equal to 1, then what do we know? So we know that A0 is 1. So we set n is equal to 0. So it is 1 is equal to, this is A times 2 to the power 0 plus B times 2 to the 3 to the power, B times 3 to the power 0. So we get the first equation, from A0 is equal to 1, we get 1 is equal to A plus B. And now from A1 is equal to 2, we will know that this is equal, 2 is equal to 2A plus 3B. Is that okay? So for this particular boundary condition, we have this is the linear equations that we can, simultaneous linear equation, 2 variables, 2 equations, and then we can try to solve it. So after solving it, maybe we get what? So we get A is equal to something like -1, and then B is equal to 2. Does that make sense? No. 1, 2, 3, 1, 2, 1, 2, no. No. B is equal to 0, A is equal to 1. Is it? Yeah, it looks okay, right? And if you have another different condition, different boundary condition, you solve for different A, B, and then you get the solution for that one. Okay? Okay, but there are some tricky things. Okay, is that okay? Let's try an example just for today. Let's try this one. So we know the Fibonacci number. 1, 1, 2, 3, 5, 8. Is that okay? So we can define this as what? F. So let's call it F0. Let's call it F1. So this is not the usual way to define. Usually we call it F1 and F2. But today let's call it F0. Okay? Okay. So we have F0 is equal to 1, and then F1 is also equal to 1. And what else? And then we have F of n is equal to F of n minus 1 plus F of n minus 2 when n is equal to greater than or equal to 2. Is that okay? We want to solve this. This is a recurrence relation, right? And what is the current? So we want, and then it is so the particular solution for this one is 0. So this is nice. So we just need to get the homogeneous solution. And that's the end. So we set up the characteristic equation. So what should we do? So this is n minus 1, n minus 2. So it is going to be x squared. So we use x squared to represent fn. We use x to represent fn minus 1. And we use 1 to represent fn minus 2. So this is the characteristic equation. Okay? Or this is, we have what? We have x squared minus x minus 1 is equal to 0. Is that okay? And then we solve for it. So what is the solution for x? Okay. So this is equal to minus -1 plus or minus square root of, is it? B squared minus 4ac. So this is going to be b squared minus 4ac. Is that okay? Divided by 2a. Is that okay? Okay, so this is equal to 1 plus square root 5 or minus plus or minus square root 5 divided by 2. Is that okay? Is that okay? So usually, so this is what? This is the golden ratio, right? So let's call one of the term, let's call it alpha is equal to 1 plus square root 5 over 2. And then let's say beta is equal to 1 minus square root 5 over 2. Then what do we know? Then we know that f of n, using this, it must be equal to a times this alpha to the power n plus b times the beta to the power n. Is that okay? Is that okay? Very easy, right? And then how do we find out what is a and what is b? Substitution. We have two boundary conditions. Check for the case where n is equal to 0. Check for the case where n is equal to 1. So when n is equal to 0, we have the left-hand side is 1 is equal to 0. So this is a plus b. Is that okay? When n is equal to 1, then we will have 1 is equal to a times alpha. Okay, a times alpha plus b times beta. Is that okay? Is that okay? And then you have two equations, two unknowns, and then you can solve it. So if you go home and solve it, then this is what we can get. This is something like f of n is equal to 1 over square root 5 times 1 plus square root 5 over 2 to the power n plus 1 minus 1 over square root 5 times 1 minus square root 5 over 2 to the power n plus 1. So it turns out that using this one, then we will have a is equal to alpha divided by square root 5, and then b is equal to beta divided by minus beta divided by square root 5. Is that okay? Just go home and check. This will be super easy, because a plus b is equal to 1. So yeah, that's it. Okay. Okay. Now there is something tricky. I will leave that after the exam. So what is tricky? So let's consider a recurrence like this. So this time let's consider a recurrence like this. Let's say an minus 2 an minus, let's say plus an minus 2 is equal to 0. Let's look at this. Then what is the characteristic equation? So this corresponds to x squared, and then this corresponds to 2x, and this corresponds to 1 is equal to 0, right? Now, repeated root. There is just one single root, so x is equal to 1. No, minus 1. Now we get into a trouble. We just have one root. So in the end, it looks like we only know that an is equal to a times the root in general. Let's say 1 root to the power n. But that is not possible. This is just having degree of freedom 1, but the original recurrence has degree of freedom 2. So something is missing. So what should we do? There must be a b here that is involved. Okay, so we will talk about this next time. The idea or the concept is really simple. So you know well. Okay, later. Okay, so we will have our exam next Tuesday. So if you have any questions during the weekend, please send us email. Yeah, we may not be able to see, but then we will try to answer your questions as soon as possible. Okay, good luck to the exam. Okay.